Hello. First of all, I'd like to thank the organizers for the opportunity of giving a talk at this conference. The title of my talk is D-modules and irreducibility results for locally analytic representations. And this is joint work in progress, in fact, with Konstantin Adakov. To fix the notation, I let F over QP be a finite extension, and K will denote an arbitrary complete extension field, which will serve as our coefficient field, and then GF denotes a connected reductive group over F, such that its base change to K is a split group. So GF might be non-split, but it becomes split over K. In the split group, I fix a Borel subgroup and its Lie algebra B, which can be decomposed into a Cartan subalgebra and its nilpotent radical. Finally, let normal letter G denote the F rational points of our group GF, which I will view as a locally F analytic group, and it comes with its locally analytic distribution algebra. And the aim of my talk is to study certain modules over this distribution algebra. To start with, I will begin by recalling briefly the parabolic BGG category. As introduced. Well, the BGG category introduced by Behlens and Gelfand in the early 1970s, and then the parabolic versions a little bit later on by Ochakarili. So to do this properly, let P be a parabolic subgroup in G with Lie algebra small p. The Lie algebra of G will be denoted small g, and in fact, I denote by P and G the base change to K of these Lie algebras. So these will be Lie algebras over K. And then the classical BGG category O is a certain full abelian subcategory of representations of this Lie algebra G. It can be described by three properties. First of all, one considers only modules which are finitely generated over the universal enveloping algebra of G. Secondly, the Cartan subalgebra should act in a semi-simple way, meaning that representations decompose over T into direct sums of characters. And then finally, the nilpotent radical should act locally finite, so locally infinite, meaning that the subrepresentation generated by an arbitrary vector in the representation, say V, is in fact a finite dimensional over K for any vector in the representation. So there's some sort of finiteness condition. Here are the first standard examples of objects in this category. So the classical finite dimensional over K, finite dimensional representations of G from a subcategory of category O. It is classical that on such a finite dimensional module, the Cartan algebra acts automatically semi-simple. But many objects in this category are actually of infinite dimension over K. So let me give you a typical example. Fix a character lambda of T and view it as a character of the Borel subalgebra B. So this gives a character of UB, which I can then induce to G, call the result M lambda. And this gives an object in category O. It's actually called a Verma module. So this is a Verma module. Verma module associated to lambda is a kind of typical object in category O. Note that, for example, the vector 1 tensor 1 generates this induced module, so it's certainly finite generated over UG. Then using a triangular decomposition for G in terms of n, t, and n minus shows that it's actually free over the universal enveloping algebra of n minus, and that implies quite immediately that it's T semi-simple. And also lambda will be the highest weight of this module. All the other T weights occurring in M lambda will be smaller than lambda. And from this, it's quite easy to deduce that acting with elements from N on it produces something of finite dimension over K. So this is indeed a module, an object in category O. Now to go from here to the parabolic version of category O is quite straightforward. So the parabolic version OP will be a full abelian subcategory of all objects in O, such that not only n acts locally finite, but even the whole parabolic subalgebra P will act locally finite. So such that P acts locally finite on M. So this is obviously a stronger condition, and so produces a smaller category. Also, increasing the parabolic will give you a smaller subcategory. And here's the standard example. So as we did for the Borel subalgebra, we can also decompose the parabolic subalgebra into a Levy subalgebra plus nilpotent radical. And then starting with a finite dimensional representation of this Levy subalgebra, finite dimensional, and say simple, for simplicity, then view this representation as a representation of the whole parabolic by letting NP act trivial. So we obtain something that we can induce then to G, called the result MV. And this is what people call a parabolic Verma module, and this is a typical object in OP. Checking that it's an OP is quite analogous to what we did above for the usual Verma module. As a finite piece of notation, I shall also need the augmentation ideal of the center of the universal enveloping algebra. So set G denotes the center of UG, and I intersect this with the augmentation ideal of UG. This will give me a certain maximal ideal of the center. And for simplicity in this talk, I will only consider modules either over universal enveloping algebras or over distribution algebras that are annihilated by M0, in other words, that have trivial infinitesimal character. This is to keep things simple for the purpose of this talk. And what is now the relation to the distribution algebra? So this comes from a result of Orlik and Strauch. I will quote only part of it, the part that is relevant for this talk. So this is a theorem of Orlik and Strauch from 2014, which says that there exists an exact functor which they call f p g prime. The prime is because it will take values not in locally analytic G representations, but in the dual category of modules over distributions. And it starts from OP, but restricted to modules with trivial character, and lands in the co-admissible modules over distributions, again restricted to trivial infinitesimal character, and has the nice property that it preserves, in some sense, irreducibility. So with the property if M is irreducible, and the parabolic subalgebra P is in some sense maximal for M, then the module over dgk that we get will also be irreducible. So this is a nice and very efficient way of producing irreducible global representations of G out of local infinitesimal information on the level of Lie algebras. Note that this maximality condition here means that P is the biggest parabolic subalgebra such that M is still contained in OP. We said that increasing the parabolic makes the category smaller, so there's an optimal parabolic subalgebra such that M is contained in OP. And if this is the case and M is simple, then its value under the functor stays simple. To give an example, if M is in fact the parabolic Wörmer module we had just 1 minute ago, and we induce it, or we apply the functor to it, then we get, actually here, I should delete the prime because I will consider this now as a local analytic representation. Then this will be the parabolically induced representation coming from the contragradient P representation of V. This is a parabolic induction. Note that since V has trivial infinitesimal character, all the T weights occurring in V are algebraic. So lift to characters of the algebraic torus, big T, and then it's easy to see from that this action actually lifts to an algebraic action of the parabolic group P, which we can then induce from here to the full group G. So we get a locally analytic G representation, and this is the value of MV under this functor. And the general value is directly related to such parabolically induced representations. So this is quite a typical case. Now, what I would like to do in this talk is to reinterpret this functor, in more geometric terms, using D modules on rigid analytic spaces, and this will allow us to first of all reprove some in a geometric way some of the results of Orlik Strauch on this functor, and possibly draw also some other consequences. So I will just try to draw some consequences. To make this a little bit more precise, we'll introduce some notation and recall some elements of the theory of equivariant D-modules on rigid analytic spaces as it was developed in the last, say, 10 years by different people. In fact, it's okay for me to just work on the flag variety, although this theory is much more general. It works for arbitrary smooth rigid analytic spaces, but for the purpose of this talk, it's enough to work on the flag variety of the group G. So here it is. X is the analytic space associated to the flag variety of the split group G. So G was our split algebraic group over K. B was a Borel subgroup. Take the quotient and then the associated rigid analytic space. This is the analytic flag variety. It comes with a continuous action of the Lie group G, coming from just the translation action of the algebraic group G on itself. And since it's a homogeneous space, a smooth space, it has a nice sheaf of algebraic differential operators. So by algebraic, I just mean operators in the usual sense, so locally on, say, affinoids that allow étale coordinates. This will be given, the local sections will be given by polynomials in these derivation, in standard derivations with coefficients in the structure sheaf of X. Now, having this nice group action on X, we can introduce for G or for any parabolic subgroup, in fact, for any closed subgroup, the category of coadmissible P-equivariant dx modules. This is a nice abelian category of all the P-equivariant dx modules cut out by this finiteness condition. So coadmissibility is something which I will not define in this talk. You can think about it as being an analog of the classical condition of being a coherent D module. So it's a local condition and it is a sort of finiteness condition. The first result I'd like to recall in this context is the equivariant localization theorem, equivariant locally analytic localization theorem, as it was proved by, it was established by Ige, myself, and Matthias Strauch, and independently also by Konstantin Adakov, which simply says that the global section functor restricted to G equivariant coadmissible G equivariant modules gives an equivalence of categories with the category of coadmissible modules over distributions with trivial central character. This is a useful tool because it allows us to regard local analytic representations as sheaves on the flag variety and then use rigid analytic geometry, in particular local methods, to analyze and study these sheaves. So this is very useful in practice. And a second result, which I would like to recall, is the so-called induction equivalence. This is a more recent result, also due to Adakov. And for the purpose of this result, we can even allow ourselves to work with a closed subgroup. So for a moment, let P just be a closed subgroup of G. And then again, I will only cite a part part of the result that is relevant for this talk. So there exists a functor which one might call a geometric induction functor from P equivariant modules to G equivariant modules, which is some kind of adjoint functor to restricting the G action to a P action, so adjoint to, let me just write raise GP. I put adjoint here, I write it in this way because the restriction functor not really preserves the coadmissibility conditions here. So it's not really a functor between these two categories. So a little bit of care is needed when formulating the adjointness relation, but this is how you should think of it. It's an adjoint functor to the restriction functor, and it has a nice additional property. So whenever there is a closed subspace of X, it's a risky closed subspace of our analytic space X, which happens to be irreducible, and whose stabilizer is in some sense large. So there will be two conditions actually. So first of all is the stabilizer Gy, the stabilizer of Y and G is co-compact in G. So the quotient of G by this stabilizer is compact. It's a compact space in the natural periodic topology. And secondly, translates of Y are either disjoint or equal. So whenever there is a non-trivial intersection of a translate with Y, then in fact this translate is equal to Y for all G. So kind of translates that kind of permuted in some kind of regular way. Then the induction functor applied to the stabilizer, which then goes from Gy equivariant modules to G equivariant modules, actually is an equivalence of categories when we restrict on the left-hand side to modules with support Y, and on the right-hand side to modules with the support Gy. The functor is geometric induction. So this is a nice way of producing G equivariant D modules out of equivariant modules for smaller subgroups by inducing them from the subgroup to G. Now I will put a star to these two conditions because I will refer to them later on. First of all, I will give you an example how this condition star appears naturally in the context of the flag variety. So for any, so let W be the Y group of G, and then for any and let this be an element, then we can look at the B orbit generated by this element in the algebraic flag variety and take its Zariski closure. This is an algebraic Schubert variety, as people call it, and pass to the analytic space. So this is this could be called an analytic Schubert variety. It's of course in general non-smooth as its algebraic counterpart. And let's consider certain Schubert varieties that come from parabolic subgroups in W. So I look at the subgroup in W generated by a certain subset of simple reflections, namely those reflections that are attached to certain simple roots. So I is a subset of simple roots. So in this notation, which is kind of suggestive, so this delta here, these are the simple roots of G. and I will be a subset of simple roots, and then this generates a parabolic subgroup in the Y group. And this parabolic subgroup has the longest element. This longest element, and then the Schubert variety associated with this longest element satisfies the star condition. For example, the fact that the stabilizer is co-compact can be seen quite directly. The stabilizer is nothing else than the algebraic stabilizer, so this will be the parabolic subgroup of G, coming from the Brujah decomposition of this parabolic subgroup. So as G is defined over K, I take K rational points, but then I will intersect back to G. So this will be the stabilizer of Y, and it's easy to see that it's actually co-compact in G, just because of that parabolic subgroup will be co-compact in the K rational points of G, just by very property of being a parabolic subgroup. Okay, now I'm ready to state the main results of my talk. So 3 main results. Well, first of all, one more piece of notation. So d cap x will denote the infinite order. So let me remind you that x is the analytic flag variety of G. Analytic flag variety of G. So it's a K analytic ridge analytic space. D cap x are the infinite order differential operators on X. So as it was introduced by Adakov and Wardsley, and also in some form by Ige, Patel, Strauch, and myself. So this is a certain sheaf of differential operators on X, which contains the algebraic differential operators. There's some sort of dense subsheaf. So locally on a small enough aphenoid, which allows for étale coordinates. So here we have some fundamental derivations attached to some étale coordinates. The local sections of d cap x are not just polynomials in the fundamental derivations, but power series in the fundamental derivations, coefficients in the structure sheaf, and not all formal power series, but power series subject to a convergence condition, which is actually very strong. So this is a Banach norm on this aphenoid algebra on the global sections of U. So Banach norm of f alpha times r to the absolute value of alpha should go to 0 if alpha increases, and this should hold for any real number, for any positive real number. So these are, in some sense, entire functions on the whole space. And given an algebraic D module over dx, I can extend scalars to d cap x. So this will be the extension functor, d cap x dxm. So whenever we have an algebraic D module on X. So for example, if the algebraic D module is coherent over dx, then this extension can be considered as some kind of completion functor. And the result will also be a coherent module. And as a second piece of notation, I shall also need the classical localization functor. So I will write log m classical localization functor. So this is the localization of a UG module M. So this is classical localization. Classical, I mean, really defined by Valens and Bernstein in the 1980s paper, and proven to be, I don't need this property actually, this final property, but it's interesting to note, proven to be a functor from, so M here, sorry, M is a G representation with trivial central character. This is an equivalence of category between UG0 modules and coherent dx modules. So this is the second tool, and well, the first result I would like to quote is an irreducibility result. So this is a theorem in progress in the sense that we're still working on a proof in full generality. So let me state it. I fix a Y group element W, then I have the analytic Schubert variety and its stabilizer. This will be a parabolic subgroup in G. I call it P. And then the statement is that the induction from P to G of the extension of the classical localization of the irreducible Lie algebra representation attached to this Weil element W is in fact, so I should make a parenthesis here. So a priori, this is a G equivariant D module over X. This is simple. This is a simple D module. So here, note that here as a piece of notation. So it's well known that the irreducible objects in category O, and therefore also in the parabolic subalgebras, can be indexed by Y group elements. So up to isomorphism, there are only finitely many, and they can be made quite explicit. So what is LW? So first of all, I introduce MW. This is a Verma module, namely the Verma module with highest weight minus W rho minus rho. So here rho is as usually half the sum over the positive roots of G. And this Verma module has a unique simple quotient with highest weight also minus W rho minus rho, and it's this simple module which I call LW. So this is a simple Lie algebra representation. So maybe I should write here unique simple quotient. Simple quotient. So it's this Lie algebra representation here that one can localize on the Flag variety and then extend scalars to D cap and then induce to G, and we claim that the result is still a simple G equivariant D module. Now the theorem is okay. So the theorem so far is okay. It's okay for G being, for example, GL2 or GL3. Or if we look at special Weil elements, if we look at Weil elements that arise as longest elements of, longest element in a parabolic subgroup. And we are confident that it holds in general. We're working on the general case. The second theorem I'd like to state, and then I will explain what happens if one takes the two theorems together. So this theorem B gives the relation between geometric induction and the Oleg-Strauch functor. So the diagram of functors, from O0P to modules over the distribution algebra with infinitesimal character given by the Oleg-Strauch functor. And then here we can go by extension and localization to the category of P equivalent D modules. From here we can use geometric induction to go to G equivalent modules, and then on the right hand side we have the localization equivalence. And in fact, this localization equivalence can also be rephrased in terms of a localization functor that makes the diagram more symmetric. So the statement is that this diagram is in fact commutative. The statement implies a substatement which says that taking a Lie algebra representation here, localizing it to an algebraic D module on X, and then extending to a D cap module, actually receives a P action, which makes it co-admissible. So as a substatement, as an implicit statement in this theorem is the well-definedness of this left-hand side vertical arrow. And the main statement here is that the Oleg-Strauch functor in terms of D modules coincides with the geometric induction functor. Now taking both theorems together, this is the upshot of the two. So theorem A and theorem B together, plus theorem B together, well, theorem A proves the irreducibility of certain induced modules, and then theorem B relates these induced modules to Oleg-Strauch representations. So it's not too surprising that they both together reprove irreducibility of the Oleg-Strauch representation F. Now here the parabolic subgroup is the stabilizer of a Schubert variety. And then here we have G, and then here we have the simple module in category O. It proves this irreducibility geometrically. And by reproof, I mean that that this result was actually already obtained by Oleg and Strauch 2014, at least in the case where the group GF was already split. And well, it will reprove these results, but of course we'd like to go beyond this case. So the representations and the irreducibility are related to properties of the Bruyère stratification Schubert varieties, Bruyère cells of the flag variety. And we like to study other stratifications on the flag variety and deduce from properties of these stratifications, irreducibility results for suitable local analytic representations. And yeah, this was all I would like to tell you today. Thank you very much for your attention, and goodbye.